it on. I just put it on. So
yes.
Okay, let me see how this appears to be. Okay, now this one is the what we wanted to stream. So tell me. Looks good. Okay, can you give us a mic check?
Check, check. Can you hear me?
Okay, can you give us a mic check?
It's 5 seconds as usual.
You cannot see me and now you cannot hear me.
No, we see and hear you well. So everything is ready. The one thing missing is that you are not still visible in this lecture room. So
That's fine.
no, you need to be visible here because there's plenty of people here too.
You don't want your camera?
Yeah, we can put that on too.
Because right now it's taking the camera from your laptop.
My laptop. Now is another one. Okay, this is that's the way we're gonna go. I think everything is ready to go, isn't it?
Yeah, if it's fine by you. Like right now, the camera for yourself is just the combination of everything.
Hey, Radu, what I need to do is that once you're getting started, I need to go and pick up the extended cable to my mic system because the rest of the class is going to be the summary what we've been discussing so far. And I need to get the cable to this.
Do you want me to go?
Okay.
If it's in your office?
Because you don't find it in my office, so I have to go there. Okay, and then but anyways, so we're gonna watching this and we're gonna make sure that it's gonna be quality. I mean, there's just any technical problems, we will jump in. Okay, guys, are you ready to get started? Respect.
Okay.
Yeah, this is okay. Rather, you're not aware of this, but this is how we're getting started each of the lectures. So this is our gangster sign. The gang that is called multi-body system dynamics. Have you heard about that?
Yeah. It's people are scared even here.
So we are, even in the US they know us, right?
And Switzerland.
And Switzerland. Okay, one thing we still need here is that we need to put you a little bit louder. So how we can do that? Just a second. I need to figure if there's any way that I can, because now it's this. Okay, can you give one more mic check?
1 2 1 2 3.
Still not.
Is it better?
No, it's not very loud. It's not super loud. It could be louder. Okay, let me see where this takes. This goes there. Where this goes? Okay, what about this?
You don't have enough.
No, okay, so I take this one off.
Yes.
All right. One more mic.
Is it better now?
No changes. So why that is not yet work? Should I change this one here?
Yeah, the speaker output should be changed to this Jabra.
Jabra.
Yes.
Okay. So is that on? That's on now.
Everything is on here.
Okay, Radu, can you give us
1 2 3.
why?
Talking about something else.
No, every single lecture is always getting started like this. So we always facing the technical difficulties, and it seems that maybe my computer is crashing now. No.
So I'm thinking that I can't recall that we
Yeah,
have any speaker.
I think it is related. I think that I can fix it here. Because what if I'm gonna do this? Is it gonna be any better? Like if no, it's not willing to change this. Okay, I have a Jabra here in a list. I just need to be able to select it. Okay, you are in a Jabra right now. Okay.
Yeah.
Okay, so put this in as loud as it can be. Very good. Finally, we're good to go. Sorry, guys, a little bit of technical hassle.
Can we
Like,
try to sound like?
can you say one more time, like how clever?
I'm gonna read the titles that I said. The open source Chrono package, multi-body dynamics, and beyond. How's that?
People are saying yes, sir. So it sounds good.
All right.
Sounds good. All right. Hey, respect. Today is a special day for us. So we're gonna get the biggest brain in the field of simulation, giving us a visiting lecture. And the biggest brain is Radu Serban. He's coming from US. So is what? So there's still a problem of some kind. It's not started. Yeah, we checked a little while ago and it was okay.
Can you just reload it once? Sorry. No, like it's frozen.
It's frozen. So which one is frozen?
YouTube.
You. So it's what?
Video is frozen.
Video is frozen.
Yes.
But I see from excellent connection.
But even here, if you say that the picture is frozen.
Picture is frozen.
Just look at Radu.
I don't understand this whole thing. Like, how come it's even possible to have something like that? Because it's actually capturing my display. Okay, now I'm sure it's coming back. Is it? Okay. Tell me, how is the YouTube official? How it looks? So it's just working on.
But
okay.
What about the sound? Because you removed the audio.
So I move the audio?
Sound okay. Now it's coming. Yeah, I believe that everything is fine. Yeah, you can.
Everything is fine.
Yes.
Finally. Sorry, Radu. Usually we are facing a little bit of technical difficulties, but not usually this much. Good news is this, that what follows after this is going to be fantastic. So it's going to compensate all the technical difficulties we faced. So I was about to introduce Radu. So Radu is coming from University of Wisconsin-Madison. And if you look at the university rankings, Wisconsin-Madison is scoring really high in the university rankings, depending on what rankings you're looking at, but typically they are within, is it like within top 20 or something like that? Okay, so within top 20. So it's one of the best universities in US, and you know that one of the, many of the good universities are located in the US. All right, so we're gonna learn something about open source Chrono software package, and this is something that you can start using whatever you want because, as the title implies, it is open source. Okay, please enjoy.
Ready to go?
Ready to go.
All right. Okay, thanks. So today we're going to talk about using Microsoft Teams and streaming on YouTube. Okay, so hello everyone. I cannot see you, but I was told that you're there. So I wanted to talk to you a little bit about Chrono, which is an open source software package, set of libraries for multi-body dynamics and more. And we'll see how far we can get into the more here. Now, Aki has asked me to give this presentation when I visited La Peranta. It was October, I think, but that was not possible. However, I think that this is a better time because he told me where you are in this class. And I think the multi-body side of things, rigid and flexible, you've covered. So we can emphasize a little bit more the things beyond that one can do with this type of software. Now, I have a long agenda here. It's quite likely that we're not going to get through all of it. But I'll make the slides available. I just wanted to give you an overview of the things that I would have liked to talk had I had the time. But anyway, the idea is I'll just very briefly tell you what Project Chrono is about. And the core of it, it's rigid and flexible multi-body dynamics. I'll tell you what capabilities we have in Chrono for that. And then I'll talk about some things that are related but slightly different, a little bit of Terramechanics to justify granular dynamics, fluid-solid interaction. And as you see, I structure all this talk around vehicle applications, not because this is the only thing that Chrono can do. It actually is being used by us and others outside our group or for many other applications. It's just that vehicle mobility applications in particular are a very good platform to showcase what one can do with such a software. Machine learning and reduced order models, some applications, I don't think I'll have time to get into those, as well as co-simulation, FMI support. And validation verification, I put it in here. I have only one slide to just tell you that it's important. But again, I'm not going to have time to get into it. Maybe before I share the slides with Aki, I will put some more in this last section so that you have them if you're interested in it. Now, before we start, let me try to put things in perspective. So this and the next one are some slides from a separate lecture that I give every now and then on modeling and simulation, very general. But I think they make some very important points, and I just wanted to start with this so that it's clear where Chrono or any software like Chrono actually comes into play when we talk about modeling and simulation. So I start with this cartoon here, XKCD. I suppose most of you know this. And this tries to make a distinction between where the assumptions go in papers that are so-called empirical studies, so experimental things that are meant to support a theory, versus what we usually do when we write papers about modeling and simulation and things like that. And what Randall did here, he said that a mathematical model is a powerful tool for taking hard problems and basically hiding them somewhere under the rug. And the idea is that if you look at any paper in basic science, the assumptions and the hard problems are listed up front in the abstract. In our case, these are usually deferred later on, usually to a section like methods or something like this. However, assumptions are always there. And what's important to remember is that your results will be only as good as the extent to which the assumptions that are built into this mathematical model and simulation codes apply to the particular problem. In other words, garbage in, garbage out. So now, this is a classical schematic of the mathematical modeling process. And it all starts trying to somehow represent and analyze a real phenomenon. And it goes through usually through creating a real world model. From this one, you create a mathematical model, which is a set of equations that try to represent the real model that you try to understand. And doing some mathematical work, whatever that means, you get a result which then you can interpret and close the loop. Now, you can do this loop for relatively simple problems only. Problems for which you can find the analytical solution of the mathematical model or do some sort of pen and paper approximation. This is very rarely the case for the problems that we're interested in. So usually this schematic is extended with a second column here, or third column if you want, that brings in technology, that brings in computer simulations. And so a mathematical model is then converted into a computer model, which is simulated, and then the computer results are, through data analysis, are converted into mathematical results, and you're back in this loop. Now, just to make it clear, this is what Chrono or any other simulation software like Chrono deals with. So in other words, the assumptions and the mathematical model are usually fixed, right? So if you talk about a rigid multibody code, you already assume that modeling your mechanical system with a set of differential algebraic equations representing the motion of bodies constrained by joints is appropriate, right? So a code like Chrono cannot help you come up with a good representation of your physical problem. You have to make sure that what the type of problems that Chrono can solve are appropriate for the physical phenomena that you try to understand. All right, so without further ado, let me tell you what Chrono is all about. So it's a multi-physics software package, right? At its core, it's a multi-physics simulation engine. It's developed in collaboration between the University of Wisconsin-Madison and University of Parma in Italy. And what's important about it, it's open source. Now you'll find a lot of commercial codes with capabilities similar to Chrono, maybe not quite all of them, but Chrono is open source, and moreover, it's released under a license that allows third parties, whether they're academic or government or industry, to use it without any problems and embed it in their own software, even if they want to sell it or things like this. The main types of physics in this multi-physics here that Chrono can deal with are multi and many body dynamics. Multi-body dynamics you already learn about in this class so far. Many body dynamics, it's our way of basically saying granular dynamics, so that we make it sound similar to multi-body dynamics, but it's granular dynamics. Then we also support nonlinear finite element analysis with very specific uses, which means very specific types of finite elements, and we'll see that in a second. And also fluid-solid interaction problems. These are problems where you want to look at the interaction between a fluid phase, be it water or some other liquid, or as we'll see, homogenized continuum soil models with solids, rigid or flexible solids, like the wheels of a car or a instrument for used in agriculture or in construction and things like that. Chrono is distributed as a collection of middleware libraries, and this is important because this means we don't have a fancy GUI or a way of modeling in a visual way. You have to write a little bit of code in which you make calls into Chrono and tell it what you want to model and what you want to solve. Chrono it's a C++, but we also have wrappers so that you can use it from Python or from C#. It's not moving. Oh, there we go. Okay, so Chrono is composed of a bunch of libraries. As I said, it's a set of middleware libraries. And we call these modules. Only one of them, this Chrono core at the top here, is always built by default. All the others are optional. And you decide when you build Chrono for yourself which capabilities of Chrono you'll be interested in, so you don't have to build the whole enchilada, you just build the things that you're interested in. Now, these modules they're all called Chrono modules, but they serve very different purposes. And so you can look at them in categories of modules. So first of all, I highlighted here, I guess this didn't download the right one. I think there are some, I thought I fixed it. But anyway, so there is Chrono Core, which gives the core functionality for multi-body dynamics and for finite element analysis. There is the FSI module, which gives the solvers the modeling capabilities and the solvers for fluid-solid interaction, a module for model analysis that allows you to do model analysis for the systems that you modeled with the Chrono Core, And actually, sensor here should have been in this category. This is a set of models for physics-based models for sensors, camera, LiDAR, and so on, that you would use if you want to put together some autonomous robot or autonomous vehicle and simulate that. These four modules, they provide different physics, right? So they provide the support for simulating different physics in this multi-physics setup. Then we have, so sensor should not have been here, we have some modules that facilitate modeling particular types of systems. So ground vehicles, it's a very common type of system, and Chrono vehicle is a module that allows you to very quickly assemble a model of a vehicle without having to worry about all the single bodies and joints and all that, which is a lot of repetitive work that you have to do if you have to build multiple models of different vehicles. So Chrono vehicle gives you an easier way of dealing with that. And parsers, it's a set of utilities that allow you to bring in Chrono models that were defined in some other external tool. For example, people in robotics like to define robots in this unified robot definition format. We have a way of instantiating a Chrono model from such a description, or from files that you may be familiar with if you use the Adams commercial tool, or for those of you interested in biomechanics, there is this OpenSim that's also an open source code. They have a way of describing the mechanical system or multi-body system representing biomechanics, really, and when we can bring these in Chrono as well. And then we have some modules that allow you to solve problems on different hardware, targeting different hardwares, different parallelization paradigms, and so on. So GPU to do granular dynamics on the GPU, multi-core to do multi-body dynamics and granular dynamics with OpenMP parallelized on a CPU. And Chrono, which is a distributed agent simulation. We use this when we want to simulate many vehicles at the same time, so that and then distribute the calculation on multiple nodes, multiple computers. Then we have some support modules for linear algebra, an interface to a solver from the Intel math kernel library, an interface to the linear solver MUMS. We have modules that are dedicated to runtime visualization or post-processing, with Chrono VSG being the newest and then the best-looking one, I believe. And then we have modules that facilitate interoperability with different other packages. For example, bringing in CAD models that are modeled in Open Cascade, some utilities to do communication for co-simulation. Again, support for the functional mockup interface to define units in a standard, the standard imposed by the FMI, and a module that allows you to communicate back and from MATLAB simulations. And then finally, these modules that take the C++ codes and wrap them for use from Python or from C#. And there is a module here that is missing. It's probably the one of the more recent ones, which is Chrono ROS, which allows interfacing to ROS2 for autonomous vehicle. All right. So, as I mentioned, in order to write a Chrono simulation, you actually have to write a little bit of code yourself. You write the main program, so to speak, in which you make calls to different libraries in Chrono, telling it what you want to model and then what you want to simulate. This is the very simple example of how you would put together something like a slider crank mechanism. You just define the bodies that need to be there, then the joints connecting these bodies, and then you just start the simulation loop. So it's pretty basic. I suspect you've been using MATLAB. So think of this as trying to solve AX equal B with MATLAB, okay? So you don't have to write the code for the solver, the linear solver that solves this problem. MATLAB provides that. In the same way, you don't have to write the code to do integration of the DAEs for multi-body dynamics. Chrono does that. But in MATLAB, you have to set up the matrix A and the right-hand side vector B and then invoke the solver, say A/B, right, to get X. Same way here. You have to write the code to specify the problem and then solve the problem, so to speak. So that's the parallel to other middleware software. All right, so let's move on and start talking about the capabilities of Chrono. And as I said, I will use vehicle modeling and vehicle terrain interaction as the conduit to walk you through the different capabilities of Chrono, only because this is a prototypical multi-physics problem. So if you think of a off-road vehicle that evolves on deformable terrain, has flexible tires, and maybe also actually it's in the process of fording a river, this would cover all the aspects that Chrono can deal with. Multi-body dynamics for the vehicle, finite elements for tires, say, maybe granular dynamics to model the terrain, and fluid-solid interaction if this happens to be, a simulation done while crossing a river. So all these things show up in this type of problem. So it's a good mechanism to show you all the different capabilities of Chrono. So multi-body dynamics. There's just one slide on this, just to tell you that Chrono is a full-fledged 3D multi-body dynamics library for modeling, visualization, and simulation. It has all the components that we would expect in such a software that you would find in any commercial code as well. So you have the ability of obviously defining rigid bodies, markers on the body, different forces and torques, springs, dampers, what have you, and joints, different types of joints that correspond to different constraints, and a few other things that I'm not going to get into detail here. Now, what distinguishes Chrono from other software is it's the care and effort that went into the collision and contact support for this. And in particular, we support both so-called penalty and complementarity formulations for frictional contact. And I'll try to get to that. Hopefully we'll have enough time to get to that point. But this is in contrast to most commercial softwares that only support a penalty approach. We also have this complementarity, and both of them have pluses and minuses, and there are problems in which one is better than the other. So that's why it's nice to have both of them. All right, so just to summarize, and I have a couple of slides with equations just so that it's not only words and pictures. These are the equations that the core module in Chrono solves for rigid multi-body dynamics. And I'm sure that you're all familiar with this. These are the index 3 differential algebraic equations for constrained multi-body dynamics that are put here in index 1, in order 1, 4. But that's all there is for rigid multi-body dynamics. Now, there is a lot of space on this slide. Is that later on we're going to add some things to this. Finite element support in Chrono, as I said, we are interested in a particular set of elements and types of finite element analysis, which is finite elements that support large displacements and large deformations. And the reason is that the original goal for having this capability in Chrono was modeling flexible tires, like you have in these animations here, which should have worked. Okay. Nonetheless, Chrono supports different types of formulations for this type of finite element analysis, both co-rotational formulation and ANCF, the absolute nodal coordinate formulation, which again I suspect you went through. What's important is that, of course, we support ways of loading these structures, both with concentrated and distributed loads. We support constraining finite element meshes in between different finite element meshes, even if they are modeled with inconsistent elements, so to speak. So that's how we could do, for example, a tire like the one here, but also have the thread modeled with solid elements. And also, you can also connect a finite element mesh to a rigid body, so that you can connect your flexible tire to a rigid wheel, and you can capture the interaction through frictional contact between meshes, finite element meshes, or meshes and rigid bodies. Equations that you've probably seen. This is just an example of a beam element here with absolute nodal coordinate formulation. All right, so I mentioned Chrono vehicle. Before I go further, I wanted to tell you a little bit what Chrono vehicle gives, right? So suppose you have to model a vehicle that is composed of some chassis with some suspension mechanism in front and in the rear. Can be a double A-arm or a Pearson strut, can be any of a multitude of different types of suspensions. You have a steering mechanism and so on. You could model all of this by yourself in Chrono, like I showed you earlier, that very simple example of a slider crank. You can do the exact same thing for a vehicle, right? But it's tedious, right? And because you have to model every single body, you have to connect them with the right joints and so on, right? And if you have to do this for another vehicle, then you start from scratch, right? What Chrono vehicle offers are predefined templates for different subsystems of a vehicle that have given topology. So a double wishbone suspension always has the same number of bodies connected in the same way with the same joints. What changes from one vehicle to another when they both use double wishbone suspension are inertial properties of the different bodies, the different geometric measurements, how far the lower control arm is from the upper control arm, and things like this. So Chrono vehicle is a set of such templates, which are effectively fully parameterized models of subsystems that you can assemble like in a plug-and-play kind of thing. And with this, you can build effectively any ground vehicle that you can imagine. Certainly for wheeled vehicles, for track vehicles, we don't have that many templates yet, but more to come. And so once you have these, of course, there are a bunch of additional subsystems that make a vehicle other than just the mechanical multi-body system. We have models for all of those, including tires, terrains, as we'll see later, powertrains, engines, and torque converters and transmissions, as well as driver models, right? So these are models of either a human or some closed-loop controller that provides the inputs, the throttle input, the steering input, and the braking input, so that the vehicle does whatever you want it to do. Once you have this, you can do simulations like the one showed here, which is a so-called RMA test for off-road vehicles. So this looks at what are the accelerations at the driver's seat when the vehicle goes over a terrain with statistically known perturbations. And this is an example of what I mean by these templates. So on the left here, you have an example of a double wishbone suspension, like the physical form of it. On the right is the corresponding template. Again, the template just specifies what are the bodies and how they're connected to each other. And then all the parameters are free for you to specify in order to make this double wishbone suspension be the double wishbone suspension on the vehicle that you're trying to model. All right. I think I have not a whole lot of time, but I didn't use more than 30 minutes, so I'm still good in my book. From now on, I would like to move to some things beyond multi-body dynamics, rigid and flexible. And for that, I like to introduce the concept of terramechanics, which is a fancy word of saying the vehicle-terrain interaction to motivate some of these other capabilities in Chrono. Okay? Now, if you are able to properly capture the interaction between a vehicle and the terrain, and in the most general case, you want to think of terrain that is itself deformable, because that's the more interesting problem, off-road, not on-road. That's relatively simple to deal with. Then you can do all sorts of interesting things. So, for example, you can start designing the vehicle so that you control the pressures and the contact patch between your tires and the terrain. You can look at vehicle performance. This is a standard way, the so-called drawbar pool, a standard way of telling you how much available power the vehicle has to do some other useful work besides just moving itself, like pulling something. You can look at the influence of tire pressure on the terrain and on the vehicle. You can look at things like the effect of multipass on the terrain, so situations in which you have like a convoy and vehicles that come behind the leader, of course, will interact with terrain that was already deformed by the leader. Even for a single vehicle, this is the case, because the rear wheels do not see the same terrain as the front wheels, because the terrain had already been perturbed by the front wheels. So all these kind of things are possible if you can capture properly this interaction between the vehicle, the running gear, whether it's a wheel with a tire or a track shoe for a track vehicles, and the terrain. Other things that you can do, you can do optimization of your design. This is an example. Some colleagues of mine looked at designing wheels with grousers for extraterrestrial rovers, like the Mars rover or Moon rovers. And they looked at 4,000 different wheel designs that are parameterized by the things showed on the left. And by simulating them and capturing the performance of the vehicle with a particular shape of a wheel, they picked up the best one, which is the one that showed on the bottom here, which they also 3D printed. Okay? So these are the kind of things that you can do only if you could properly capture this interaction between the vehicle and some deformable terrain. As I said, that's the more interesting problem. So in Chrono, we have 3 different ways of doing this. One of them, which is arguably the most accurate one, is so-called granular dynamics, or discrete element method, in which you effectively model every single particle of soil. Right now, of course, that's a long discussion here. It's computationally untractable to model very, very small particles, so usually look at lumps of such particles. The problem is that this is accurate, but it's extremely costly. So the thing to look for here is this RTF value. This is called a real-time factor value, which tells you how many seconds of simulation you need to simulate 1 second of real time. And for granular dynamics, it's not uncommon to say 10,000. So you need 10,000 seconds of runtime to just see what happens in 1 second. Okay? Expensive, but in some situations, the only thing that gives you the proper accuracy. There is something that more recently we've been looking at and piggybacking here on the fluid-solid interaction module, which is a a continuum representation of granular dynamics. We call it CR or CRM, which is based on homogenization of the constitutive equations. And here you look at the soil as a fluid, very viscous fluid, obviously, with internal friction and strain stress constitutive equations that captures the same physics as the granular dynamics. So this is very promising because this one gives you accuracy comparable with full granular dynamics, but at a fraction of the cost. So you'll see simulations later on, hopefully, that show that a single four-wheel vehicle on such deformable terrain that runs like 30 or 40 times slower than real time. Okay? And then we also have a semi-empirical approach, which is this SCM, soil contact model, which in this case for this Curiosity rover, Mars Curiosity rover, is probably around 10 times slower than real time, but for a regular four-wheel vehicle, it actually runs in real time or faster. So you can actually do interactive driving this vehicle on deformable terrain and getting the feedback that the deformation of the terrain provides. Of course, this is a much simpler model and it doesn't capture all the physics that you want. So you always have to compromise between accuracy and computational cost, typically. All right, so Aki, if you can hear me, can you give me a rough estimate of how much more time I have?
Aki is not here.
No. Oh, okay, so then I have 2 more hours. Someone, can you tell me when does the class end?
No, this ends at 6 o'clock our time. It's 5 to the 5. But the thing is that there's also another subject matter we need to discuss today. And,
yeah, I understand that. So I'll probably try to go through a couple of things, and I leave, as I said, the machine learning applications and the co-simulation and share the slides. And okay.
Machine learning would be really nice.
So let's talk a little bit about granular dynamics because it's a very interesting topic, and I hope that some of you will get interested in this and work on this. So in Chrono, we can do granular dynamics, DEM, with at least 3 different solvers, right? One of them is in this Chrono multicore, in which we can do any simulation of any multi-body dynamics mechanism, like we do with the core of Chrono, and at the same time do granular dynamics. And we have this parallelized through OpenMP to use the many cores that are now available on modern processors. Now, of course, this is relatively limited in terms of performance because there's only so much that you can get from, say, a processor with 20 cores. But it's still a very nice option, especially when you want to solve the granular cross multi-body problem as a monolithic problem all at once. Okay. The other nice thing about Chrono multicore is that it supports both the penalty and the complementarity approach, which I'll go into in a few slides. Both for the mechanical system itself, but also for the frictional contact between all the particles in the granular terrain. Okay. Now, to squeeze more performance from these solvers, we have codes that run on the GPU, right, and take advantage of the parallel architecture of the GPU and do granular dynamics on the GPU. The original GPU code, this Chrono GPU, was able to deal only with particles that were the same shape and size, and in particular spherical shapes. And it was based on using a single GPU using CUDA. And the simulation here in the middle is done with this Chrono GPU. Now, in the last few years, we had a student who just defended his PhD, and his work was on on extending this original GPU code to allow it to work with particles that have different shapes and different sizes, and also squeeze in more performance by using two GPUs if they are available on your machine. If not, it falls back onto using a single one. And you see at the bottom here a simulation of the Viper lunar rover on a particular type of granular terrain that NASA uses to do their experiments. And as you can see here, I hope the shapes are different and different sizes. So that's definitely a accuracy improvement of this DME code over the original Chrono GPU. And the use of two GPUs also gain some performance. So what is the problem with granular dynamics? Now, we said that we can do multi-body dynamics, which is constrained multi-bodies. Well, if we can do that, for sure we can simulate single rigid bodies. That's much simpler. And we already said that we know how to deal with contact between different shapes. Well, that's true when you deal with a handful of bodies. However, if you want to solve a problem like the one on the right here, where this one I believe had, I don't know, probably 2 million particles on the right here in this hopper, the problem becomes much more complicated purely due to the sheer size of the problem that you have to solve. So you need to do something smarter than just brute force approach. There are two main formulations for contact, the ones that I mentioned before, and I want to talk about them here. The first one is the so-called smooth contact formulation. Now keep in mind, let's disregard finite element for a second, and we're talking only about contact between the rigid bodies, right? Now, the smooth contact formulation, which is also called soft body approach, but soft not in the sense of finite element or penalty-based, says something like this. Suppose you have two bodies that come into contact. Well, you relax momentarily the assumption of rigid body and say, I'm going to allow the shapes, the geometric shapes of these bodies to overlap a little bit. And I will use the amount of overlap to come up with some nonlinear spring damper force model that will try to separate, to prevent these bodies from further interpenetrating. So this is the smooth contact formulation. It goes back quite a while, and many codes, most codes actually use this approach. One of the big problems with this one is that contact materials are typically stiff, and this translates into stiff numerical springs, which result in stiff equations, which require small integration step sizes, and hence long simulation times. Now, an alternative to this smooth contact formulation is non-smooth contact formulation, in which instead of relaxing the rigid body assumption, you actually embrace it and you say, let's formulate the contact force model such that we impose the condition that two bodies cannot possibly penetrate because they are rigid, right? Well, in this case, you can do this, but mathematically you end up with a problem which is a different animal now. It's not a DAE anymore. It's a so-called differential variational inclusion problem. And the result of this is that in order to solve this type of problems, you actually end up having to solve very large optimization problems. So there is no free lunch. As I said, in one of them, you have to spend a lot of time because you have to use small time steps for stability reasons. In the other one, you don't have these stability reasons. You don't have these very stiff virtual springs in between two particles. But you have to spend a lot of time because you have to solve very large optimization problems every single time step. Now, both of them require collision detection because in order to generate contact forces, you first need to figure out when two shapes actually touch or are about to touch, and this is a purely geometric problem. I don't even mention it in this talk, but this deserves a talk by itself. The non-smooth contact, as I said, also requires optimization techniques because of these optimization problems that need to be solved. And both of them obviously require numeric integration because at the end of the day, you solve the Newton-Euler equations to move the dynamics of the entire system forward in time. This is a quick schematic of the smooth contact. It has a kinematic aspect to it, which is the geometric problem. Given the current positions and the states of the two bodies that can potentially interact, you want to find this overlap here. And then it says the kinetic aspect, which is the contact force generation process, in which you take this interpenetration and look at it as some deformation in springs, right? Normal and tangential to also capture friction. And there is a plethora of different formulations for these normal and tangential spring dampers here. And as I said, this has been around for a long time. The original paper was this paper by Kandel and Strack Bacon in the late 70s. On the other hand, the non-smooth frictional formulation starts with this assumption: I cannot let the two rigid bodies penetrate. So what does this mean? This means that if you somehow are able to define a so-called separation function, this phi here, which always measures the distance between the two closest points on the two bodies, you distinguish between two cases. One is this distance function is strictly positive. In each case, it means that the two shapes don't touch each other, which means that the contact force is zero. So if the gap function phi is strictly greater than zero, then the contact force, normal contact force, is exactly zero. On the other hand, when the two shapes touch each other, then the gap function becomes exactly zero. And in this case, you have a contact force, which is by convention, picking the sign that you like, it's always positive, right? So at the end of the day, you have these conditions, which are called complementarity conditions. You have a contact force that is non-negative, a gap that is non-negative, and their product must be zero, but they cannot be zero at the same time. And mathematically, this is written in this shorthand form with this complementarity condition, this operator, complementarity operator. This is why the non-smooth frictional contact formulation is also known as a complementarity condition. Now, what's interesting about this? Remember the equations of motion that I showed a while ago, only for multi-body dynamics, you know, your typical rigid body problem with joints, meaning bilateral constraints, right? Joint constraints here, and the Jacobian of the constraints that comes in with some Lagrange multipliers. Well, if you want to work with frictional contact in this non-smooth approach, then you need to introduce these complementarity conditions for each contact, and these are unilateral constraints because the two shapes are constrained only in one direction. They cannot penetrate each other, but they are free to separate. So these are different types of constraints than the joint constraints. And because they are constraints, they come with their own Lagrange multipliers. And then if you also want to introduce friction, then the problem becomes even more interesting because you need to introduce some sort of constitutive law, a relationship between the normal contact force and the frictional force. Typically, this is done with Coulomb friction. And Coulomb friction, the way you know it from high school or undergrad courses, can actually be re-expressed in the form of this maximum dissipation principle. So you can write it as an optimization problem. The friction forces are the ones that minimize this thing here. And this introduces its own Lagrange multipliers. Now, when you look at this problem, this is not a DAE anymore. This guy here was an index 3 DAE. This is not a DAE anymore, the big problem, because it has these unilateral constraints and because it has this optimization problem hidden into it, right? And then remember, this is done for every single contact, these two. And just one slide to, again, cover a lot of work and a lot of presentation material. The way to solve this type of problems is by converting them to some problems that are solvable, because the DVI problem by itself, there is no numerical method to solve it. But what we can do is we can convert it to a so-called cone complementarity problem, which then we convert to a quadratic problem with conic constraints. That all you hear cone in this slide, you have to think of the friction cone. That's where these constraints come from. At the end of the day, you have to solve one big optimization problem at every single simulation time step, in which the size is like 6 times the number of contacts. And just to put things in perspective, these are the sizes actually here. If you think of simulating 1 cubic meter of sand that has about 1 billion particles, a particle typically has about 6 contacts active at any time. So any single particle is in contact with, on average, 6 other particles. So you have 6 billion contacts, and you have to solve an optimization problem that is 18 billion unknowns. Once you solve it, you get all the contact forces in between all the particles that are in contact at once, right? And then you can just do simple integration to advance the time once you have these contact forces. But this is very expensive, okay? So this is just a slide to summarize the two different approaches. As I said, none of them is the best, right? You cannot pick one. They have pluses and minuses. For example, the smooth contact problem has some issues with selecting the step size, stability issues. It also requires you to know the history of contact. So when two bodies come into contact, you need to keep track of that contact from time step to time step if you want to get the proper physics. On the other hand, the non-smooth complementarity has the problem that it has to solve this humongous optimization problem, and it also cannot model certain phenomena. For example, shockwave propagation through granular material, because it solves the entire problem at once, right? So it cannot get this delay of propagation through granular medium. And I'm going to stop before I show you some simulations and some applications. I just want to also to pique your interest in this type of problems, to pose here a mental exercise, right? So here's the thing that we're trying to solve. We are not interested in what happens between any two grains of sand, right? What we're interested in something at the vehicle level. So like this Curiosity rover here going on a slope, a sandy slope, right? So we're interested in phenomena that happen at the scale of meters, right? Human scale. However, in order to capture accurately the physics, we have to do this by falling back onto microscale dynamics. So we need to be able to figure out exactly what happens between any two particles for all of them, so that we get the emergent behavior at the vehicle scale. Now, here's an interesting problem, okay? So let's take some physical quantities that are relevant in this problem, thinking that we will do a penalty method. So we take a stiffness, all SI units. Typical stiffness of rock or steel or any hard material, it's of this order of magnitude. Here is a density that, again, is typical for silica. And now let's say that we don't do this on Earth, but rather we do it on the Europa Saturn moon. And as is typical of regolith, which is the dust on extraterrestrial dust on moons or extraterrestrial planets, they're much finer than the sand on Earth. So 10 to minus 4 meters, which is only a tenth of a millimeter, is nothing uncommon. So, and now think of this problem, the one that's down here. I need to figure out what is the force that develops between these spheres so that the 4 bottom spheres support the top one, right? Now, you can imagine this each grain is very, very light. And not only that, but we're in a very low gravity environment. So the force that needs to be developed between any two of these are tiny. And in a penalty method, these forces are generated from this interpenetration, right? So the question is, how small of an interpenetration do I actually need between, say, this ball, top ball, and this one here to generate the tiny force that is needed to support the top ball? And if you do the calculation, you see that the deformation is of the order 10 to minus 18 meters. This is ridiculously small. It's below what the guys who do molecular dynamics deal with. But more importantly, it's below the accuracy with which you can represent numbers on a computer. So it's impossible to actually solve this problem with floating point arithmetic on a computer, okay? And actually think of that this was Europa, which has the gravity only, 8 times lower than on Earth. But if you want to do this on even smaller moons, you can work with gravities that are 1,000 times smaller than what's on Earth. So on top of all of this, because these are very stiff, you also need to evolve at very small steps. But the interesting thing is this one. How do you deal with these small numbers? And here's what is done in the GPU codes in Chrono, which are meant to be used for this type of simulations. Well, effectively, we don't work with floating point numbers anymore because we saw that there's no computer that can do this efficiently. And so what we do is we use only integers, and we represent any location or dimension in the problem with integers, because there is no loss of representation accuracy when you use integers on a computer. And this is done in a hierarchical way using a couple of longs and a short, and this gives you the position. So all arithmetics in these GPU codes is done in integers, and only when you need the final answer is converted back to floating point numbers, because at that point you are actually back in this regime that you are interested in. Okay. I'm gonna skip fluid solid interaction, unfortunately, because there is no time. Just go quickly through some simulations here. Different ways of dealing with this. So what we solve there is effectively the Navier-Stokes equations. We do that with smoothed particle hydrodynamics. And to solve the actual coupling of the two phases, solid and fluid, we use an approach based on so-called boundary constraint enforcing markers. And we pose the problem as a big co-simulation problem between the solid phase, think the wheels of a vehicle, and the continuous phase, whether it's continuous granular for when you do the soil simulation, or if it's fluid, if you do water simulation. And just to show you one problem that I'm actually working on right now that is not vehicle based. This is some problems that we try to help people solve in marine energy. So this is a wave energy converter device. So the thing on the left here, it's a piston that moves back and forth to generate waves. And the actual device is this one here, which is spin down here and is moved by the waves. And from here, you can harvest energy. Skip this. And let me just finish with a few examples, right? So the type of problems that we can solve with Chrono, remember when I started saying that vehicle mobility is a prototypical multi-physics problem? This is such a problem solved here. So it's a vehicle with full multi-body dynamics, flexible tires interacting with granular terrain and other objects. So this is something that you can solve with Chrono. This is some work that we did a while ago for NASA and JPL. They built this simian robot, and they were contemplating different ways for it to move itself. Of course, driving it's pretty simple on the wheels, but it has this walking, this inchworming, and this sculling where it moves like a snake or something. And the question was, which one is more energy efficient? And we were able to simulate this and extract the reaction torques at all the joints and give an answer. This is an example of the Viper rover moving on an incline here. This is actually an incline, you don't see it, but this is done by tilting the gravitational vector. And this was done on this Glenn Research Center 1 simulant, which is a model of lunar soil that is appropriate for experiments on Earth. This is what NASA uses to design their physical and test their physical rovers. And this is what we simulated here with this DME new GPU solver. Another interesting problem, you've seen this, oops, that's not what I wanted to do. Oh no, this is definitely not what I wanted to do. Let me try to get back to it.
So, Radu, you wanted to say something about the technical problems and how you are never suffering from any of those stuff?
I did not say that.
Well, you were making fun of my technical skills. I think it is my time to do an exercise.
Not only that, but now I cannot restart it for some reason. This is insane.
Tell me about it. Tell me about it.
This is us.
Yep.
I don't get this.
That's when we are putting the highlights of your lecture, you're not able to share it with us anymore. So what happened? I heard, by the way, that today is some kind of like not a good day for Microsoft. Microsoft is suffering for all kind of difficulties. Is that?
Yeah, I know. It is, isn't it? Ah, there you go. It's coming back.
Hold on. We are in a.
I think.
You are not sharing. You're not.
I'm not sharing, right?
No, you're not sharing.
I will take care of these technical problems in a second.
Yeah, but the thing is that I can kind of do this. Oh, you go now.
Yeah. Okay. I need to get to where I was though, and wrap up. Yep. So let me just say that last thing here, and I'll wrap up. Even know where I was anymore. Oh yeah. So you may have seen these pictures in the news that the Curiosity rover had all these issues with the wheels being come on. With damage to the wheels, right? And this is because there is no traction control on this thing. So the 6 wheels all move at the same angular velocity. And this is a problem when the rover starts going on inclines, because at that point, some of the wheels should turn slower than others, right? So what we did through simulation, because we didn't have access to Mars or the Mars rover on Mars, we did this in Chrono with a model of the Curiosity, which you've seen before, and models of this continuous representation of granular terrain. And we designed different traction controllers for them. And we show that actually we can save energy with that, and also decrease the slip at all the wheels, which is the direct, it can be directly related to damage to the wheels, right? The more a wheel slips, the more damage it incurs. So that's also an interesting application. I mentioned earlier that we can do simulations of, it's a bit choppy, the animation, but so this is a Polaris vehicle that evolves on deformable terrain with this controlled statistical deformation on the top. This is a standard mobility test in vehicle dynamics. And this was done on a single NVIDIA GPU, of course, an A100, which is a little bit of a more expensive one, but still one desktop with one GPU. And it was only 36 times slower than real time. So to do, I don't know what long, this is probably like 5 seconds. It took 5 times 30 seconds. So really not that much. You can also, of course, do flexible tires on terrain and some other applications of, these are proper fluid here. This is water. You can do fording simulations or sloshing simulations. So I'm going to completely skip this machine learning thing here and ROMs. I'm going to skip the co-simulation. And I just want to stop at the last slide, which is this one, because I didn't put any material here. And just end with a warning that a code is only as good as it can be validated, meaning it needs to be a predictive tool. It needs to be able to reproduce reality. And as such, you should never trust numbers or plots or pretty animations that come from a simulation until you also see validation studies for that one. So, and again, I could probably speak a couple of hours about the work that we've done in Chrono to validate it, the different types of physics and the coupled and all that, and that's an ongoing problem. But it's critical, and I didn't want to have these slides without at least this cartoon to show that. So with that, I'm going to stop. And here are some links if you want to learn more about Chrono, look at the implementation, download it, build it, test it, get involved in the user forum and discuss about it. I'm available and really happy if any one of you is interested in this and reaches out. And I'm also visiting La Peranta a couple of times each year, and I'll be there sometime in the spring. So if you want to talk more face-to-face. Till then, I'm going to stop and let you do the, what is it, a recap session, Aki?
That's going to be the recap. So let's give a big hand to Radu. Thank you. So Radu was a little bit shy that he did not mention that he is officially affiliated in LUT. So he is a team member.
I put it on my slides, very first one. You didn't mention it.
Ah, okay. Okay. Anyway, so thank you very much. So what follows is we need to have a short break. I need to change the setup to such that I can stream this using my presentation instead of Radu's. So thank you, Radu. Can we get these slides? Can we put this in our...
Yes, I'll add a few more in a few days. I'll send them to you, okay?
This is not going to be public website, but it's going to be something that the students only can log.
I don't care. Open source. Everything is open source. The slides included.
All right. Thank you. Thank you very much.
Thank you for having me. Bye.
Bye. Okay, so guys, so 5 minutes and I need to do a little bit of changes to my setup. And then we're going to do the recap. And then that's it about the technical matters. The last thing to do is carry a counseling in a week from now. Not mandatory to participate. Very good. So it's already sound on. So then this one on. Can you check like how is my voice?
Yep.
And it's very good. Very good. Very loud and clear.
Yep.
Loud and clear.
Yep.
Okay, so we have 24 slides to go. I think that I need to be fast here, so I cannot really spend too much of the time for this recap and other practical matters, but yep, I'm gonna be fast. Doable. Yep.
How big the simulation applications in Finland?
How big is the simulation?
Industry.
Well, yeah, so that's a good question because it's not this like this guy, Dorado mentioned that he's collaborating with NASA and other organizations like government organizations. So in Finland, it's not that. It's not that. It's like the companies that are doing the heavy machinery, like the ones that are like Ponce, Sandvik, Kone, Crane, stuff like that. Companies like that. Cargotec.
They're mostly like dealing with like steel structures and the.
Yeah, it's like a heavy machinery. So that's a little bit different than this special application of like this, but the kind of the vehicles that are sent over the Mars and how they perform there. So that's very unique.
And I heard about that one of the reasons like most of the steel structures that they are finished, most of them because the application of the industry.
So the steel structures are finished?
No. Most of the students, there's Finnish students studying civil structure and welding. Most of the time.
Really?
Yeah,
So the international students are not selecting that discipline.
Last year, not anyone.
Really?
No one.
So what is that? Why?
Because I know the reasons.
So, okay, so but the streaming is on. So you guys, if you know the reason, you keep it better. Keep it in your private.
So is everything okay? Because based on that YouTube, I heard that you had some problem.
No, it's okay. It's okay.
Okay.
It's okay. Oh, by the way, the one thing is missing here is my camera. The camera is not in so OBS.
I'll have to disconnect this one.
No, I think it is okay. It was just that.
No, for this one. Now this one is connected.
Oh yeah. What is this? This is my mouse. The cable is not connected. Okay. So let me see. Video capture device. Is this a HP? The one that's
No,
HP.
this is Dell. HP
That's
is
Dell.
your laptop.
Dell. All right, so it's Dell.
Yeah.
Yep, and it's looking good already. It comes with a little bit of delay, but it's okay. You guys, I'm curious to learn about the reason, but don't tell me now because the streaming is on. So, but I want to discuss once we close the streaming later today. So if this is if you can share this information with me, I would really appreciate that. Yeah.
As we heard about like last.
Oh, no, you don't need to mention, but we discuss later. We discuss later.
All right.
Hey, it's another. This guy is. another 25 minutes.
Okay.
25 minutes, and then we good to close. Less, 20 minutes. 20 minutes. 20 minutes. Okay, Team Finland is coming back momentarily. All right, 20 minutes. Okay, guys, so one more thing we need to discuss, and that's a summary what I'm expecting you to know in the next midterm exam. All right, extremely critical. Yes, it is true that the next midterm exam is easier than the first one. But what you should learn from that, you should understand it in a way that now is your opportunity to score high from this class, because you work like no limit and you're going to get the good grade from the second midterm exam. Remember, the midterm exams are summed together and we're computing the average. So you need to perform well from both of them. So they are equally important. Now the second one, if that is easier in terms of subject matters, then it really makes sense to put full steam ahead. I mean, put all your effort to second midterm exam, because that's where you can score higher probably than the first midterm exam. Okay, so do your best, and I trust you're gonna do your best. All right, so we're gonna discuss about the recap. So we're gonna discuss about the summary. Next week, that's gonna be the last week we're gonna meet in this class. So please come here in person, because as promised, the first thing we're gonna do in the beginning of class, we're gonna go to get some coffee from cafeteria, on me. All right. And then we're going to discuss about career counseling, which is not a mandatory subject matter. But as I promised to Mustafa, it's only going to be 20 minutes for the recap. So we discussed about flexible bodies a week ago, and we concluded that the flexible bodies can be categorized to different categories based on how large is a deformation. Mathematically, it's about how you describe the relation between the displacement and strain. Displacement is that if you look at the free end of the cantilever beam, how much that is moving from the original configuration. That is displacement. And the displacement, as you can imagine, is a function of the length of the beam. Because if you hear, the deformation, the displacement is zero, so it's non-existing. But further off, you're going to be from this place, then it's going to be different. So how are you relating displacement and the strain? And if you relate those things to be linear, then you are limiting yourself to small deformation, which is okay, but then it means that this free end of the cantilever beam stays on the loading line. That's okay assumption, but you understand that if the deformation becomes to be large, this is not realistic anymore. Another source of linearity is a relation between the strain and the stress, which is a material nonlinearity. We haven't discussed that at all. All right, so that was about the flexible bodies. And then you know that this can be, I introduced you to two different ways to describe it. The one that was not really the base, is what wasn't really the formulation based on flexible multi-body dynamics, but more like an application of rigid bodies. Because here you take your beam-like body, typically you limit yourself to beam-like bodies, and replace that by multiple bodies. And between the bodies, you can introduce the spring elements, and then it behaves kind of like a deformable body. Or alternatively, you can get this deformation from a finite element model. And when you do so, then you're going to use a method that is called floating frame reference formulation. This is a method that I will introduce you to the best course in this university, entitled Simulation Laboratory course. As I also will explain, what the heck is the deal with this smooth and non-smooth dynamics, something that Radu mentioned in his lecture. He spoke about this cone complementary. We are not going to go details in the cone complementary or the non-smooth dynamics, but I'm going to explain where it is actually needed and what's the concept, what's the principle behind, and how the smooth dynamic works and where you can use that. And that's all related to contacts, and contacts are related to games. So game technology is one of the largest field of industry that is looking for contacts. Rally games, shooting games, you probably don't need much of a contacts, but there are many other games where the contacts playing a major role. So we're going to learn that. All right,
So that was the flexible bodies. So why this is making this noise to me? All right, we are covering only 3 subject matters for the next midterm exam. Embedding technique, which is not very important, so it's rated as 3 stars. Hydraulics, which is the primary, the main body that you need to master when you enter in the next midterm exam, and deformable bodies, which is the lowest ranked subject matter. So put all your effort to hydraulics. That's something that I'm expecting you to master when you're getting into the next midterm exam. All right. Please remember this. This is the picture that this is what we learned from the first lecture. So written exam is not the whole everything that you can do. It's just a part of it. It's 1/3 of the grading. Then there's a weekly homework, which is a little too late to do anything in this regard. Simulation work you can do quite a bit, and this is also getting too late to do anything at all. Now here's what I would like to propose. Like discussed a week ago, it was originally mentioned that next midterm exam will be organized in week 50. And I don't have a calendar with me, but week 50 is what is it? It's a December, second week of December, if I remember correctly, isn't it? That's the case? And my proposal is this. Let's organize the exam in 2 weeks' time. 2 weeks' time, 2 attempts. You can make a first attempt in the beginning of week 49, and then the second and the end of the week 50. So now if somebody can double check to me, when is that the week 49 is getting started? Is it getting started next week? 2nd of December. That's what I was hoping. Yeah, 2nd of December. So next week, Monday, when you're going to see me in this career counseling, the midterm exam is already on. And you have 2 weeks' time to make it happen. How that sounds? All right, good. Now why this is back? So embedded technique is this story. We use the concept of virtual work, virtual displacement, and we were able to express external applied forces and inertial forces in equilibrium like this. This is external applied forces. This is, by the way, everything that I explained here. Let me get started. Everything that Radu explained, you guys know it already. The notation he used was a little different that I have used to deal with. Because he was telling about the equation of motion, you can say, yeah, I know it. That's my middle name. I know equation of motion back and forth. He was explaining about these Lagrange multipliers. Yes, I know this. I heard about it like a million years ago. I know this very well. So you guys are not aware of this thing. What is confusing, that he used a little different notations. All right. I was about to say that we use the concept of virtual work to get this equilibrium equation. And now as virtual work is expressed here, we cannot say that this equation is equal to 0. What's the big problem here? Big problem is this virtual displacement that is imposed to all the generalized coordinates and is not obeying the constraints. So not okay. And because of that, this equation is going to be non-zero. And what we will do is that we will force this virtual displacement to be expressed in such a way that is kinematically possible, admissible. And when we do so, then this equation can be set to be equal to 0, and we can get rid of this virtual displacement. Okay, how it goes? It goes in by using method based on the coordinate partitioning. Coordinate partitioning, you're dividing your coordinates into 2 different categories, dependent and independent. How? Well, you can do the selection as you want, but in a computer software is made by using Gaussian elimination with the full pivoting. But you can do it when you do the exercises, you can do it as you want. And then you're using this coordinate partitioning in your Jacobian matrix, and that allows you to relate all the coordinates and independent coordinates. And that's what allows to express this previous equation such the way you set that to be equal to 0. Then a couple more additional notations, and you can write your equation of motion like this. And during the weekend, I got very very surprising email from one of you guys saying that I have a mistake in my lecture note. And every time that you say that there's a mistake in my lecture note, and the mistake is not that you don't like the content, but there's a technical mistake, that makes me very, very happy. And this student was able to detect that there is a mistake in my notation. There was a typing mistake, which I'm going to correct, but not this class. And there was something, if you look at my lecture note, there was the D matrix was incorrectly written. So you need to take that into account if you're going to use my lecture notes. Fantastic. I'm sure each of you are studying my lecture note, these details every evening. So where the laugh? So you guys are not? Anyways, but one only was able to see this problem. All right, back in hydraulics. So these are the things that I'm expecting you to master. Properties of fluid, LAM, fluid theory, flow types, modeling of hydraulic components. Those are the things. All right. Annoying thing. Okay. Properties of fluid. Two things only that you need to know. There's viscosity, which is not very important. So if you are busy, forget about it. The bulk modulus, you need to understand what that is representing. You need to also understand what is an effective bulk modulus. So you need to understand that that's the same that elastic modulus, expressing flexibility of hydraulics. So the lower the value, more flexible is your hydraulics. And bulk modulus and the viscosity is something that you better understand in detail. Bulk modulus comes from this kind of the exercise when we look at the two containers that are combined together, such that there is no pressure losses between these two containers. And with help of this exercise, we were able to express something that was called effective bulk modulus. Effective bulk modulus is something that takes the flexibility of all the components into account. All right, and how you can write this in details was this. It was based on here in 3 components: flexibility of fluid itself, flexibility of the first container, this one, as a container, and the flexibility that the second container as a container. The same way you can take the hose lines and others into account. All right. LAM fluid theory. That was this first order differential equation that described the pressure as a function of time. So it was this P dot. Remember, it's not the pressure, but it's a P dot. And the equation went is such the way that it's getting started by first expressing the effective bulk modulus divided by volume size, flow rate in, flow rate out, and then the last component was how much possibly the volume itself is changing as a function of time. All right, flexibility, volume size, flow rate in, flow rate out, and then how much the system is changing. And when you do this, you need to first divide your hydraulic circuits within the volumes where you are assuming pressure to be equally distributed. Why? Because you're only using one differential equation. So it cannot understand that in within this volume, the pressure is different in different locations. That's not possible because one equation only. That's a limiting factor. All right, and this is how it reads. So this is what I already put in the writing. Make sure that you understand the concept itself. Okay? And then the components. Well, not components first, but the flow types. So there are 2 different flow types that in modeling perspective behaves completely differently. The first one is a laminar flow, not very common, where flow rate and the pressure difference are linearly related. This is where the viscosity is actually playing a role. So in only flow type, the viscosity is having any kind of role whatsoever is this laminar flow. Not common. This only takes place when pressure difference is small, which is unclear statement. Let's say less than 5 bars, less than 2 bars, which is not common in mobile machinery. In turbulent flow, pressure difference and the flow rate are quadratically related. And that's pretty much what you need to know. And when you look at this analytical equation about the flow rate, the viscosity is not here. So it's not counted. All right, valves, modeling of valves consists of two parts. First, you need to know how big is the throttle itself. And once you know that, then you can model the flow rate through it. Sometimes in some of the simple components, like poppet valves, throttles, there's not really a need to do that kind of computing because the valve is either fully closed or fully open, or is all the time open, and the throttle diameter is not changing as a function of time. But other components, you need to understand where is that this moving component is moving, and based on that, you can define how big is the throttle size. And then you can model the flow through your component. All right, and the method we use is based on the semi-empirical approach, where we're gonna get started from analytical equation, modify it in a way that unknown parameters are combined, and more importantly, are in a form that you can get it from manufacturer's catalog. Simple example is this. So this is a throttle valve equation, analytical expression. You take these parameters, replace them by one parameter that you can get easily from manufacturer's catalog. Same way for direction valves and other other components. And here is your direction valve. This is a good example about where there is two steps. First step, you need to know where the spool is located at, and that you can define by using this first order differential equation. And based where that is located at, you can have a different flow equations. Look at this. So laminar flow is not accounted. So we are assuming that the flow is all the time turbulent. Sometimes, yes, it helps to have this laminar region because that makes it numerically to be more pleasant to deal with. All right, then hydraulic cylinder and a pump. Remember that the pump, is assumed to produce flow rate. This is a little bit of chicken egg. So the pump is producing flow. And when you're limiting the flow, you get the pressure. This is how it's being understood in a modeling perspective. And we can have a different kind of pump types. We can have a constant volume pump, and then we can have variable volume pump. Variable volume pump adjusts how much flow it is producing. This adjustment can be based on load sensing, or it can be constant pressure control. There's a multiple different ways how that can be accomplished. All right, you're producing the flow in your system. The flow is restricted. That introduces the pressure. Pressure goes all the way to your hydraulic cylinder, and that converts this kind of hydraulic pressure to be the mechanical force. How? By pushing this piston right side, such the way that the pressure that is applying in a piston here is that the cross-section area is multiplied by the pressure. That's going to be the force that is moving this direction. It is also resisting by pressure that is in a piston rod side multiplied by corresponding cross-section area. The one thing that needs to be accounted is a friction that is coming because of the sealings. Friction, if you look at that, how efficient is a hydraulic cylinder, is only like 5% as a rule of thumb. Deformable bodies, remember this. So we have two ways. Don't put that much of an effort to this because it's not so important in this class. We will get back to this a little later. All right? And then comes this. And now this class ends. Respect. Class ends this, but we're gonna see on Monday. I mean, you don't need to come if you don't want to have a coffee, or if you don't want to care about the career counseling. You can have them both or one. You can come, skip the coffee, learn about the career counseling, another way around. Let's go home. Okay, thanks guys. Let's go home.